What if the coldest place ever created isn't drifting in deep space, but orbiting just a few hundred miles above our heads? Not on a distant frozen planet, not near a dying star, but inside the International Space Station, where a tiny box creates temperatures colder than anywhere else in the known universe. This is the story of NASA's Cold Atom Lab and how it's changing our understanding of reality itself. In our everyday lives, cold is just the absence of heat. But in physics, cold reveals something much deeper. As you lower the temperature of something, its atoms slow down. The frantic, random dance of particles begins to quiet, the universe's background noise fades, and if you get cold enough, right at the absolute edge of what's possible, nature starts to behave in ways that defy all common sense. That edge is called absolute zero, the theoretical point where all atomic motion stops completely. It's the ultimate stillness, and the Cold Atom Lab was designed to get closer to that point than ever before. Launched in 2018, the Cold Atom Lab, or CAL, is a marvel of engineering packed into a container roughly the size of a suitcase. Its mission sounds simple: make atoms really, really cold. But the reason it's in space, on the International Space Station, is what makes it so revolutionary. Here on Earth, every experiment is fighting against one constant, relentless force: gravity. If you try to study a cloud of atoms, they fall. They bounce off the walls of their container. They settle at the bottom. The experiment is over in a fraction of a second. But in the microgravity of orbit, atoms can float. They can be suspended almost perfectly still for far longer than is possible on the ground. And in that extended stillness, entirely new physics begins to emerge. Just how cold are we talking about? Deep space, far from any star, is cold. It's about minus 270 degrees Celsius, or just 3 degrees above absolute zero. The Cold Atom Lab goes incomprehensibly further. It uses a combination of lasers and magnetic fields to slow atoms down, chilling them to just billionths of a degree above absolute zero. At these insane temperatures, something extraordinary happens. The atoms enter a bizarre and wonderful state of matter, first predicted by Albert Einstein and Satyendra Nath Bose back in the 1920s. It's called a Bose-Einstein Condensate, and it's where our understanding of the world starts to break down. Think about atoms as tiny, individual marbles. Normally, they bounce around, they collide, they act like distinct objects. But when you cool them into a Bose-Einstein condensate, those individual identities dissolve. The atoms lose their boundaries and begin to overlap. They synchronize. They start to behave not as a collection of separate particles, but as a single, unified quantum wave. It's like a crowd of people suddenly moving and thinking as one single being. This allows scientists to observe the strange rules of quantum mechanics on a macroscopic, visible scale, something that's almost impossible under normal conditions. And in space, these condensates can last for many seconds, a virtual eternity compared to the fleeting moments they exist on Earth. In the world of quantum physics, those extra seconds are everything. One of the most mind-bending tools inside the Cold Atom Lab is something called an atom laser. But instead of shooting out beams of light, it emits controlled, coherent streams of atoms from the Bose-Einstein condensate. These aren't just streams of particles, they are matter waves, behaving in ways that let scientists probe the very foundations of physics. They use these atom waves to test our most fundamental theories. Does Einstein's theory of general relativity, which governs gravity on the large scale, still work perfectly at the quantum level, or does it break down? So far, the answers are incomplete. And that uncertainty, that gap in our knowledge, is exactly what the Cold Atom Lab was built to explore. On Earth, our measurements are always limited by gravity. The atoms we're studying simply fall too fast, and the experiment ends before we can get the precision we need. In orbit, the Cold Atom Lab can observe these free-floating atoms for up to 10 times longer. That extended period of observation allows for measurements of extraordinary sensitivity, unlocking the potential for future technologies we can currently only dream of. Imagine navigation systems so precise they never drift, or new ways to search for mysterious forces like dark energy, which is pushing our universe apart. By pushing atoms to the limits of cold, we are pushing physics to the edge of what we know. The Cold Atom Lab isn't looking for aliens. It's not taking breathtaking pictures of distant galaxies. Its mission is more fundamental. It's asking, what are the true rules of matter? Are the laws of physics that we've discovered just approximations, valid only in the warm, noisy, chaotic universe we're used to? Or do they hold true under all conditions? In the quiet, ultra-cold environment of the lab, physics whispers its secrets instead of shouting them. And sometimes, it's in that whisper that you find the deepest truths. Orbiting silently above us, this small, unassuming box is exploring questions as old as time itself. It's a reminder that some of the biggest discoveries aren't made by looking out, but by looking deeper. Here, we explore the cosmos not just through speculation, but through the real experiments and hard data that reveal the universe's greatest mysteries. Because sometimes, to truly understand the universe, you have to create a place colder than space itself. Thanks for watching. If you want to explore more of the science happening at the edge of human knowledge, make sure to follow along for our next journey.